Hey, thanks for the introduction. I'm Xupeng Miao, and I'm currently an assistant professor at Purdue University. I'll be the presenter of today's tutorial. First, I want to say that I really appreciate everyone's coming and getting up so early. I know it must be exhausted because some of you may have already here for after many hours flight. So I'm hoping that everyone here has already take a great sleep so that you can be ready for this tutorial, okay? This tutorial is about a very timely topic about how to serve generative language models efficiently. We intend to provide a comprehensive overview of the latest advancements in this field, no matter on you have which kind of machine learning research background. We hope that even non-specialists can follow along this easily. Okay? Quick summary of what happened in the past 2 years. Generative language models like ChatGPT have become a driving force behind significant advancements in AI and demonstrated remarkable progress on a wide range of tasks. And there are more language model applications on other domains beyond language tasks, such as personal copilot, art creation, and robot control. Given the increasing diversity of these applications, it would be natural to expect that the model architectures used in deep learning would be some more diverse, but the opposite is happening. Transformer as a game changer was first proposed by the paper Attention is All You Need in 2017. After that, Transformer has become everywhere within 3 years. For example, computer vision, audio analysis, and many other application scenarios started to use transformer model architectures. This table summarizes some latest language models and their model structure details. But if you look at them, we can find that all these models are sharing similar model architectures and with only some minor changes of the architecture configurations. More specifically, you can find that all of them are using similar architecture, but only some different hyperparameters, like the number of attention heads, the hidden dimension, or the choice of positional embedding methods or activation functions. But basically, all this transformer decoder architecture is the same, and it has been used for many popular language models. So, if you have ever used any of existing language model service, you might also know that almost all of them are generating output tokens step by step, which is called autoregressive decoding. So each output will become the input context tokens of the following output tokens. So we will go through these details in the following slides. So given the great success of language models and their widespread development in real-world applications, language model serving is a new research direction which aims to help people to solve the deployment problems for language models in production environments. As a middle layer, it maps the gap between these models and the underlying computational resources and will become more and more important. Another proof here is that if you look at the recent computer system conference, almost everyone will provide a dedicated session on language models with a particular emphasis on serving systems due to the increasing importance. Another proof is that the computation between different language model API providers is more and more fierce. They not only consider the model output quality, for example, the average score on several reasoning tasks, but also consider the inference efficiency and the cost effectiveness. For example, these 3 figures list some popular language models and their rankings. As we can see, GPT-4o has the best output quality, and similar, we can find the speed and the price of GPT-4o is much higher. So these large companies have provided some lightweight language models to help achieve some benefits on the efficiency and cost effectiveness, like the latest GPT-4o mini, which is much smaller but have a lower price with a small degradation of the model performance. Okay, in this tutorial, we will first introduce a lot of recent techniques on LLM serving. But before that, I would like to list some key challenges we should keep in mind in today's tutorial. The first challenge is about the latency and the response time. Large model serving usually needs a low latency and fast response, especially in some real-time applications like chat robots, virtual assistants, and interactive systems. And different approaches may prefer different metrics when evaluate the serving system. For example, the time to first token and the time per output token during the decoding phase, and also the end-to-end latency, which is the sum of the TTFT and TPOT. And also some research which cares more about the real-time system experience. We also measure the minimum token delivery speed. Actually, this is a really funny metric because it's related to how humans read and understand language. Like different age group people may have different speed of understanding, reading these tokens. And also different languages may also have a different speaking speed in terms of the tokens. The second part of the key challenge is memory footprint and the model size. We all know that large models with billions of parameters may require a collection of GPUs to serve them. For example, for the 175 billion GPT-3 model in high precision, we need at least 10 A100 GPUs. Another important part is about QLL cache. I guess many of you may have already heard this abstraction. Basically, it's proposed for accelerating the computing process of the autoregressive decoding algorithm, which means that you don't need to recompute previous generated tokens, context information, and you can reuse these intermediate results, and we call this keys and values KV cache in existing serving systems. And with the growing need for the long sequence inference, the memory footprint for the QL cache stands out as a prime optimization target compared with the model weights. For example, if you look at the OPT30B model, and if we increase the sequence length or the batch size, the QL cache can easily exceed dozens of gigabytes for GPU memory. The third key challenge is about scalability and throughput. Inference systems often face varying levels of request loads in production environments. So we need to guarantee their scalability and throughput to handle multiple simultaneous requests efficiently. And there will involve a lot of optimizations in several aspects. And the fourth thing is about the hardware and the accelerators. So today we have already successfully deployed large language models on many other types of accelerators beyond the GPUs. For example, our laptop and even the edge device can still run some small size large language models. So this kind of optimization requires some hardware-aware algorithm design and optimizations to exploit the potential computing capability of these devices. And next point is the trade-offs between accuracy and efficiency. If you look at this recent language models public service, you can see some leaderboards or benchmarks on comparison between their accuracy and efficiency. So actually, it's very important to know when you are optimizing the language model serving system, you need to guarantee the output quality is not reduced. So basically, considering all these kinds of challenges in different aspects, first I want to say that there's no one-size-fits-all solution. But what we want to discuss today is trying to tell people, actually, we can already make great progress on optimizing partial of these automation targets. Okay, now let's move on to the main part of today's tutorial. I will first provide our taxonomy of existing approaches on efficient language model serving, and I will revisit these related works from two aspects, including algorithm innovations and system optimizations. The difference between these two aspects is that for the algorithm innovations, we mainly focus on changing the algorithm execution logic, and the later one, system optimization, will not change the algorithm execution, but only optimize underlying system. But please keep in mind that these two aspects are not independent. For example, when you are optimizing the algorithm, when you are designing a new model architecture, it's better to also consider the underlying system execution for better end-to-end efficiency. Okay. So during this process, I will also highlight four of our recent work, and I'm hoping that these examples can help you have a better understanding of the research directions in this field. Okay, here is the taxonomy of today's tutorial, and the main content have been put on a survey paper before, and it's on archive half a year ago. But considering this field is moving so fast, so we made some updates in our survey paper and also in this tutorial to keep track of these recent advancements. So just before, if you have read our survey paper before and found some misalignments, okay, we will also update the survey paper very soon. Okay, the first part is about the algorithm innovation, and as we mentioned before, part one is to address the native performance flaws of large language models through the algorithm advancements. And the first thing we want to discuss is the decoding algorithm. A major limitation of large models is the default autoregressive decoding algorithm. As we mentioned at the very beginning, it will sequentially generate output tokens one by one. So each token generated is conditioned on the understanding of all previously generated tokens. It allows language models to produce highly relevant and contextually appropriate text sequence. To address this problem, one representative line of work is to abandon the autoregressive generation paradigm and decode the output tokens in parallel. So it's called non-autoregressive decoding, which is first proposed in 2018 for machine translation acceleration by breaking the word dependency during decoding and assume a certain degree of conditional independence. So here we use a table from another survey paper which already collected dozens of non-autoregressive decoding algorithms. Actually, this paper comes even before the explosion of ChatGPT. So which means that if you read some latest papers on arXiv talking about how to generate tokens non-autoregressively, please remember that it's not something new because there are a lot of existing approaches in this direction. But unfortunately, until now, due to the unawareness of the conditional dependence between the output tokens, the output quality of most of these methods have still been less reliable than the autoregressive decoding methods. Okay, the third one is called early exiting. This study attempts to utilize the deep multi-layer architecture of existing large models and leverage the early exiting mechanism to accelerate the decoding process. The intuition is very easy. For example, some simple tokens don't have to pass through all these layers in the language models. So after, for example, 1 or 2 layers, we can already make sure that it will be correct. So we can directly generate the tokens. But this may also affect the output quality. Okay, the next one is called speculative decoding, which is also the most promising direction in this field. So here we would like to introduce one highlighted research in our past projects, which is called SpecInfer, which is the first tree-based speculative decoding system for language models. And this paper is also accepted by S+ this year. Okay, so we have already shown that existing language models are using an incremental decoding approach. For example, in this figure, each decoding step only generates a single output token, and using the input prompt and operators generate tokens. And during each step's calculation, most operators will be the product between a small token vector and the model weight matrix. So with such a fine-grained GPU kernel execution mechanism, it's very hard to fully utilize the GPU compute resources. On the other hand, incremental decoding also requires to access all model parameters and the kernel cache to decode a single token, which makes the decoding process highly memory bounded. So before introducing our solution, there is also another important observation worth to be mentioned is existing public language models are usually released with several variants in different scales. For example, the smallest GPT-3 can only has, like, for example, 125 million parameters. It shows pretty low model performance on different text generation tasks, but it can be hundreds of times faster than the largest 175 billion model. So considering these pros and cons, we would like to ask the following question. Can we achieve the best of both and build a cheap, fast, and accurate M-serving system? A promising alternative solution is called speculative decoding, which was first proposed by Google and DeepMind individually at the end of 2021. So they are also called sequence-based speculative inference, which involves an additional small model as a speculator. The speculator is responsible for taking a quick guess on the next few tokens during the decoding process. For example, in this case, the small model will try to predict what will be the next 3 output tokens. And the second step is called verification, because the speculation can accelerate the decoding process, but it may not guarantee the correctness. The verification, which is made by the original language model, will try to check whether the output tokens correct or not. So in this case, we know that the first 2 tokens are correct, and we can send these verification results back to the speculator and continue the speculation and the verification process until all the output tokens are generated correctly. However, this approach is difficult to achieve significant speedups in real-world applications due to several practical challenges. Here we list mainly 3 practical challenges. The first one is how to make the speculation fast enough, because the speculation of a small model due to the data dependency will also block the execution of the verification process. So ideally, we want the small model or the speculator with nearly 0 time cost. And second is the verification process. It should also be efficient. It may not be as efficient as the small model because we are using the original language model to verify the tokens, right? But for example, if you want to verify 3 tokens, it should be faster than 3 decoding steps by using auto-regressive decoding. And the third point, which is also the most important, is the speculation should be accurate enough. For example, in an extreme case, each step speculation always gives you wrong prediction. Then the verification process will digress to the default autoregressive decoding because it will only tell you 1 correct token in the next step. Okay? So now I will explain our solution called SpecInfer, and we propose the first tree-based speculative inference system and algorithm to overcome all these problems. Specifically, we have two key techniques. The first thing is called a learning-based speculator, which is to generate speculated tokens fast and accurate. And the second is the tree-based verifier, which will verify the token's correctness efficiently. The basic workflow of spec infer works as follows. The speculator takes a sequence of tokens as inputs, but unlike previous approaches where the speculator outputs a sequence of tokens, here we produce a speculated token tree. Note that a sequence is also a special case of a tree, but the goal here is to maximize the overlap between the predicted tokens and the language model's original output. So we support two different methods here to generate the tree. The first one is called merge-based methods, which relies on multiple diverse small models and merge their predictions. Our experiments have observed large speed-ups when we involve more small models. And another method here is called expansion-based token tree construction method, which means we can only use a single small model, but during the decoding process, we will use like top K sampling method to track multiple prediction branches. And as we can see, when we increase the tree size by increasing top K from 1 to 5, which means that we select the top 5 candidates at each step by using the small model and verify the output tokens, then we can achieve nearly 96% acceptance rates for the next token prediction. So basically, the how to expand the token tree is an open problem, and there are a lot of following up work in this direction. So I think it will be much more promising if we have better GPUs in the future, because it will provide much more zoom for the speculation process, and it will not block the verification. After the speculation, we will send the output, the predict token tree into the verifier. And the first step is to linearize the output tokens into a sequence and verify them in parallel. So by default, if we want to reuse existing language model serving systems, a very simple solution is still use the sequence-based verification GPU kernel. It will generate all paths in this tree structure using different GPU kernel calls. And that will be very inefficient because it will involve some redundant decoding computation. And if you have much more requests, it also costs a lot of your kernel cache due to the GPU memory limitation. So to do this more efficiently, we introduce a new operator called tree attention. This operator takes a tree of speculative tokens as input and produces an output that is equivalent to the running attention on using the original autoregressive decoding approach. The key optimizations here is first, we use a depth-first search to linearize the token tree, and we will not store all this redundant GPU the redundant kernel cache of these tokens. And for example, in this case, there is a path from T2, T3, T8 to T9, and all these prefix tokens will only be stored once. And we will also introduce a topology-aware causal mask to identify which tokens in this continuous kernel cache memory space will be accessed when verifying this sequence. And in this way, all these tokens in this tree can be verified simultaneously. So our experiments have used several public available datasets and shown that our system can be at least 2.3 times faster compared with existing systems. Here we evaluate on different environments like single GPU, single node, and multiple GPUs, and even multi-node. And we have compared with, for example, VLM, NVIDIA's faster transformer, and also Hugging Face TGI. And we also create a baseline by using spec infer, but run the default incremental decoding approach. And then you can see that by introducing our tree-based speculative decoding approach, we can achieve very significant speedups on all these different scenarios and models and data sets. We first released our paper in May 2023 and open source our code called FlexFlow Serve. And the repo has been started for more than 1,000 stars in GitHub. But what is much more important here is that our paper is the first to produce the tree-based speculative decoding algorithm, and we found that after 4 months or since our paper release, almost all of these released papers in this field are starting to use this kind of tree-based speculative decoding and tree attention to speed up their algorithm execution. Okay, that's a quick summary of the first highlighted research in our past projects. And the next thing in the decoding algorithms is called cascade inference. And this technique also introduce another small model or even more small models. But the execution flow can be different. It will first try to identify whether the input query or the input token is difficult enough to use the large language model. If it's very easy, we can just use a small version language model to get the outputs. So the key challenge here is to design the classifier about how to determine whether we need to use the large model. So this is also a very interesting direction. Okay, now let's move on to the architecture design of the large language model serving. The first thing is, if we want to improve the large model serving system efficiency, we can directly, a straightforward approach is we can directly downsize the model configurations, such as using shallow structures, for example, using less model layers, or we can enable people to share weights across layers, or you can also shrinking the embedding table size. Another important direction is called attention simplification. This is because we know that the self-attention calculation has n-square computational complexity with respect to the input sequence length. Okay. Actually, even before 2022, numerous transformer variants have been proposed to simplify the standard attention calculation for more efficient alternative solutions, such as sparsification, kernelization, and factorization. And recently, there is a trend of borrowing the ideas from prior attention simplification approaches to generalize and combine them to shorten the context and reduce the kernel cache size, as well as the attention complexity. We have listed some examples here. For example, if you have heard about Cedarhands and H2O, which are using some selective kernel cache or selective attention calculation techniques for generative language model serving, but actually it has already been studied a lot in previous, for example, informer or top K attention research. Okay. Similarly, for example, there's another very popular project called streaming LLM. The key idea is try to prioritize the initial token of each query and also some recent tokens in the sliding window, which has also discussed in some related approach like sparse transformer, longformer, and star transformer. We have also studied the relationship and the development of these techniques in another survey paper. And if you have interest, you can take a look at them. And the key finding in that paper is that we found that these different approaches will simplify attention significantly different. So it will have unequal time cost or memory usage in practice. And more importantly, there is no such thing as a free lunch, because these optimizations have sad effects on the model performance in varying degrees. And due to the incomplete context and the complexity of attention distributions, these approaches may also face inevitable information loss in real-world applications. Okay. The next part is called accuracy sharing. For example, by default, we use the multi-head attention calculation, but some people have proposed to use like a grouped query attention technique, which allows to share partial keys and values between a group of queries. And in the multi-query attention, all these queries will share all these values. And in the multi-layer MLKV approach, it even able to sharing key values among multiple layers. And maybe you have also heard about some public language models which have already started to use this kind of optimizations. For example, in Falcon and Pell model, they are using the multi-query attention. And in the Llama 2 and the Mistral 7B model, they are using the group query attention. The next part is called conditional computing, or more specifically, it's called the sparsity activated mixture of experts models. MOE models is trying to partition a model's capacity across various experts, which are just some smaller neural networks, and each expert will have some specialized skills in different subsets of the data. And during the inference process, only a few experts will be activated, so the time complexity will be lower than the default language models. And this figure also shows that actually there are a lot of existing public language models have already starting to use mixture of experts architectures. Maybe you have heard some of them like Mixture and DeepSeek. And they can also show very great performance on some language model benchmarks. The last point in architecture design is called using the recurrent unit design in transformer models. Actually, the recurrent neural networks has a competition with transformer architectures many years ago, and recently people trying to reuse the recurrent unit design is because of I think it's mainly because of the efficiency problem. And there are a lot of related approaches you may have heard before. For example, RWQV, RedNet, and even like state space models called like Mamba. Their design is composed of various various techniques, not just the recurrent unit design, but also like the better precision encoding modules and like the exponential decay mechanisms, and also more importantly, a stack of token-wise nonlinear MLPs to improve the model representation capability. Okay, that's the last point of the algorithm innovation is called model compression. And the basic idea is trying to use smaller models for the language model inference. And the first technique is called knowledge distillation. And based on the different way we distillate the knowledge from language models, there are two categories. One is called the white box knowledge distillation, where you have a teacher model and you can access the model parameters. And the second thing, which is much more interesting recently, because there are a lot of public language model APIs, but you cannot access the model parameters like ChatGPT or GPT-4. So what people are doing is trying to record all the response and inputs of this language model service, and then you can use these pairs to fine-tune your own smaller size models. For example, ARPCA and Vacuna, which are just some representative approach in this direction. And the next part is called the network pruning. Actually, this line of work have been extensively studied in the past few years, but not all of them can be directly applied to language models. For example, the unstructured sparsity approach may not very easy to apply because it's very hard to achieve real-world speed-ups in practical systems. And also, for the structured sparsity, it has a very great assumption, but it may not be real in practice. So a better solution might be using some like a semi-structured sparsity. Another advantages of this other approach is it can lead to very significant inference speedup by using NVIDIA's sparse tensor cores acceleration. Okay, now we have already finished all these algorithm innovations, introduction of recent advancements, and move on. From now, we will move on to the system optimizations, which is personally, I feel like it's more exciting to introduce. Okay, and this part is about, as we mentioned before, it's about investigating the serving system optimization techniques to accelerate inference without modifying the LLM computation semantics. So the first part is called low-bit quantization. I think many of us who have deployed learner models in practice have already enabled this feature, but you may have you have no idea about what happened inside this optimization. So basically, it's trying to use fewer bits to represent numeric values, and these models will have less memory consumption and much efficient execution on GPUs. So the first line of approach in this direction is called post-training quantization, which is mostly used by existing serving systems. And the PTQ will try to reduce the computational precision of model weights and even the activations into lower precision. For example, here W4A16 represents we compress the model weights into 4 bits and compress the activations by using FP16. And this kind of approach is also supported by the underlying hardware. And the evolution of this hardware is very important because, for example, if we look at the NVIDIA's recent architecture, Turing and Ampere, which has been introduced int 8 and int 4 tensor cores. And in Hopper architecture, it has disabled int 4, but it introduced another FP8 tensor cores for better numeric precision. And if you look at the latest Blackwell architecture, it even supports FP6 and FP4. It has a larger range of numeric value representation. And when people are doing these quantization methods, you need to also think about whether you want to use a uniform quantization or non-uniform quantization, or a symmetric or asymmetric quantization, and this may also affect your final model performance. Actually, there are a lot of other other directions in quantization because, for example, some of them will try to quantize the model during the training process, and also there are some people trying to use the quantization to reduce the color catch size, which is called context quantization. And also, during fine-tuning, we can also introduce the quantization techniques to accelerate the model execution, no matter on fine-tuning process or the inference process. Okay, and the next part is called parallel computation, which means that for language models, by default, we try to support the execution of language models by introducing multiple devices. And a very important line of approach is called model parallelism, Basically, it will try to partition the models into different devices. And this approach is first proposed by distributed training of large language models. For example, in tensor model parallelism, we split the model layers into multiple pieces from internal dimensions. And another important approach is called pipeline model parallelism. It will put the model layers in a sequence across multiple devices, and each device is responsible for a pipeline stage that consists of multiple consecutive model layers. So these approaches actually have already been studied in training systems in the past few years. For example, like Unity, ARPA, and Gauchon have already covered almost all of the parallelism dimensions when we're trying to partition the models. So the question is, what's the difference for language model serving? One big change here is that for training, actually, due to the large volume of input data, we usually use a very large batch size, and we expect to use some expensive super GPU clusters to produce language models with higher training throughput. But for inference, it's totally different. Most people use language models may just have a very small or very low input workload, which means that serving usually have fewer running data samples, and it can be deployed on smaller sized GPU clusters with lower costs. So that comes to our second highlighted research. It's called Spot Serve. It will tell us how to reduce your language model serving costs on much cheaper devices. Here we call it preemptible instance. Okay, so the first question we want to answer is why language model serving is expensive. If you compare with, for example, using the public language model service API from ChatGPT with just run the open source models on cloud GPUs, you will find that the costs are actually very similar. So basically, almost all of these costs are coming from the GPU resources. But most people are using these cloud GPUs by using on-demand instance. An alternative solution here is called spot instance. And for example, AWS, Azure, and Google Cloud, all of them will provide spot GPU instance, which can be at most 10 times cheaper than on-demand instance. Another proof is that people found that in the past half year, the spot instance price for A100 GPUs have already dropped 70%, just because of the more and more people are providing GPUs. Right? So that's a very great alternative solution. But it's more affordable, but it also has some problem. It's because of the preemption. For example, here we show a real 24-hour trace by running spot instance on AWS. On average, preemption will happen once after every 5 minutes. So in the worst case, it will even happen every minute. It means that when you are running your language model serving systems, some of your GPUs might be they disappear because of the cloud scheduler. So it will also terminate your currently running programs. So that's not what you want in practice. So that's why we propose our system called Spot Serve, which can support to run your language model serving systems on this preemptible spot instance. And the benefits is that by introducing some optimization techniques like reparallelization and context migration, we can actually significantly reduce your tail latency, but also achieves much cheaper price compared with on-demand solutions. So let's start with the first question is, what will be the issue when preemption happens? Here we can show a real example by running a language model by using 4 GPU instances. Here we use a very simple parallel solution, just like using 2 pipeline stages, and for each stage we use tensor parallelism with a degree of 2, which means we have 2 shards for each stage, and each GPU will be responsible for one of them. And when we start the serving system, the request will be calculated by this instance following the pipeline dependency. And for example, in this case, the preemption happens at certain timestamp, and what will happen now? The problem is that the inference request R1 will be interrupted. And another issue here is called chain crashing, because both the data dependency in pipeline model parallelism and the collective communication in tensor model parallelism, they do not naturally provide any fault tolerance. So if the second instance is preempted, all the other 3 instances will also be terminated during the inference process, and the preemption can potentially hand all the other instances in the same inference pipeline. And the affected instance will not be physically terminated, but they will stay idle until new instances are allocated to establish the new inference pipeline and continue the inference process. So during this whole preemption happen and recovery process, we can find that the instance preemption will have 2 issues. One issue is that it will interrupt the running request and increase your inference latency. Right. But another problem here is that during the handling of these preemptions, your system throughput is also lower. For example, if you have much more input arrival rates at this time, and your system cannot consume them efficiently, then it will have some accumulated requests, and their scheduling overheads will also be parts of their inference end-to-end latency. So how to handle this problem? The opportunity here is by utilizing the grace period provided by the cloud service. Modern clouds will usually notify the users about the preemption happen, for example, 30 seconds before. And we can utilize this grace period to handle these preemptions efficiently and reduce our tail latency. But actually, the grace period cannot directly solve the problem because the time window is too small to, for example, reload all these model states because of the limited network bandwidth. So here we want to introduce a proactive preemption handling method. The first thing we want to use is called dynamic reparallelization. We know that people have already developed several distributed serving systems to parallelize your language models. But during the preemption happens, what we need is we need to adapt to the new instance of availability and adjust the parallel configuration based on the current available instance to achieve better parallelization performance. Note that finding the right parallel configuration is non-trivial because it's related to the trade-offs between the inference latency and the throughput. For example, pipeline parallelism will slightly increase inference latency but leads to a very high throughput. On the contrary, tensor model parallelism reduces the latency but also involves some overhead to the throughput. So here we propose an adaptive optimization algorithm to find the optimal solution in response to both the dynamic instance availability and the fluctuating inference workloads. The following question is when and how we should change the parallel configuration. We introduce the context migration algorithm to solve this problem. We may not want the reparallelization happen after the preemption, because restarting the whole cluster can be time consuming, as we mentioned before. So we would like to opportunistically reuse some of existing GPU memory contexts rather than just destroying them. So here, the contexts include both the model parameters and the kernel cache. So in practically, we want to migrate this context information among these live GPUs to finish the reparallelization process before preemption really happens. Considering the model is partitioned among GPUs, so how to decide the migration plan is also a problem. Although we get the new parallel configuration, but for each instance, we still don't know which topology position in the new parallel configuration will be the right migration target. So here we introduce a graph matching algorithm to achieve efficient configuration transformation. The key idea is to formulate the mapping relationship as a bar graph and the migration overheads and as the weights of the edges between the original position and the target position. Then we can apply the KM algorithm to figure out the optimal migration plan with minimum migration overheads. Another advantage of context migration is that we can easily resume the interrupted results from the migrated kernel cache, since it's already migrated in the GPU context information. Combining all these techniques together, we build the world's first linear model serving systems on spot instance, and we evaluate on real traces collected from AWS. And in addition, we are also wondering, what if we allow users to mix up the usage of both spot instance and on-demand instance? It's reasonable because sometimes allocating spot instance can be difficult. For latency-sensitive scenarios, you may want to allocate on-demand instance immediately to maintain your service quality. So based on the spot instance traces, we generate two new traces by allocating on-demand instance when preemption happens. And we build two baselines. One is just do reparallelization, but without any context migration. Another one is much simple, just reroute all these interrupted requests to the other inference pipelines. But for the affected preemption instance, we will just wait until new instance join to restart the inference pipeline. And we also evaluate on several different models and different inference arrival patterns. And we can see that no matter on which kind of model and workloads, we can achieve very significant speed up and reduce the P99% tail latency by up to 9.1 times compared with our baselines. And what is much more important is that our system can help to save up to half of your money costs on compared with the on-demand GPU instance, but without sacrificing your inference latency. And this system has also been open source and achieved the Distinguished Artifact Award. And so if you have a chance, you can have a try to save your money. Okay. Okay. The next line of approach in parallel computation is called decentralized inference. It's highly related because it also introduces a combination of model paradigm or data paradigm in distributed environments. But the difference is that here we may use some geo-distributed resources. Actually, it's inspired by, for example, crowdsourced computing. Here, like Petals, which serve Bloom 176 billion model using the collaborated community GPUs over the internet. But actually, the decentralized inference is very challenging, and somehow it unlocks the overlooked consumer level GPUs to run large models. But you know, like in practice, we have very heterogeneous GPU devices, and the network connection is not stable, and the connection bandwidth is also lower than the company GPU clusters. So we need to consider these problems when we design our language model serving systems. In this figure, we show a case that we have 5 nodes in 2 clusters, and in region 1, we have A100 GPUs, which is much more powerful, and on region 2, we have a mixture of L4 and T4 GPUs, which are much weaker than A100. So if you want to deploy the language models on these heterogeneous devices, it's very challenging because you may easily suffering from like the workload balancing problem or the congestion conflicting problem due to the network bandwidth. So we have recently published a work called Helix, which try to model this problem as a flow-based serving scheduling problem and optimize this problem in terms of both the model partitioning and the request scheduling. And as a result, we can achieve a network-aware placement plan to maximize the throughput and minimizing the inference latency. Okay, the next part for the system optimization is called memory management. As we mentioned before, the kernel cache is a very important factor in the consideration of building language model serving systems. And as the kernel cache memory grows and shrinks dynamically during the incremental decoding process, the naive approach, which is used in like a faster transformer, will pre-allocate a continuous space of memory and with a maximum sequence length of the generating assumption. So that kind of approach will waste a lot of GPU memory because the input batches may have different request lengths, and the outputs can also be very complex in different decoding scenarios. For example, if you use like beam search or parallel decoding, you will have to copy the memory space multiple times. So in VLM, they propose page attention that partition the kernel cache into non-continuous memory blocks and improve the batch size as well as the throughput. Similarly, in spec infer, we also introduced the tree attention GPU kernel will remove all the redundant token kernel cache storage by using the depth-first search approach. And another work here is called light LLM. It targets the issue of page attention by using a more fine granularity, which called token level memory management mechanism to further reduce the memory wastage. And note that the overheads of such fragmented memory managing also introduce new challenges, especially for the case where the other optimizations are deployed to improve the batch size, for example, concatenation or model compression. Then the fine-grained memory management methods might only offer marginal throughput benefits, while it will substantially increase the inference latency. So to address this problem, V-attention is proposed by rewriting all the underlying memory management operations by using CUDA native APIs, and it also implements a virtualized memory manager to replace the paged manager in VLM and improve the memory utilization. The second line approach is trying to figure out the common prefix in the output tokens, and we can eliminate that redundant memory usage. For example, in VLM and it's following up SGLang, there has a lot of applications that, for example, you have a very long chatbot history, and there might also exist some different branches, and some of them may share the same prefix. So we can just keep one piece of the kernel cache without any redundant storage. And also in spec infer, when you are evaluating the tree-based speculation, there will be multiple output sequences actually, but you can just store one piece of this prefix tokens in kernel cache. And if you have much more resources, hardware resources, you can actually scale up or scale out your kernel cache by introducing this more hardware. For example, you can use CPU memory or even SSD to store this unused kernel cache during the inference process. While representative work is like infinite gene, which is presented in this year's OSDI. And also, if you have more GPUs, it's also possible to distribute the kernel cache on several GPUs. And representative work like ring attention and deep speed, and they try to distribute the attention calculation along the sequence dimension. So in this way, the kernel cache are also partitioned along this among these GPUs. The next direction is called disaggregation. It's similar to scaling out, but there are some differences. For example, there are several ways to disaggregate kernel cache. One is just people have found that the computing property of the inference process can be different at the prefilling phase and the decoding phase, because the prefilling phase has a very long input sequence, but the decoding phase will only generate a single token. So they try to propose a disaggregated architecture to put the inference process of the prefilling process and the decoding process into dedicated GPU resources. For example, in this figure, there will be a separate instance for the prefilling stage, and also another instance for the decoding stage. And the inference process will be executed sequentially across these two instances. And there is another way of disaggregating is like just disaggregate the kernel cache from the running instance. And that can also be scaled on like CPU memory or SSD. Representative work in this field like infinite LLM and long serve and mooncake and attention store, and all of them are trying to disaggregate kernel cache from the computing GPU resources. The next part of the system optimization is called request scheduling. Request scheduling for language model serving, actually it shares some commonalities with general machine learning serving techniques, and they are both aimed to efficiently manage the incoming requests and optimize the resource utilization. Some early language model serving systems like faster transformer only support request level scheduling, which is similar to prior approaches. And Orca first noticed the gap between the generative language models and the request level scheduling of previous machine learning inference system. So considering the variable input sequence, the variable output sequence length, it will schedule the execution of the execution engine at the granularity of iteration with a first come first serve order, and enable the balance of selected operations for better hardware utilization. The thoracic serve splits the input prompts into uniform chunks and piggybacks the chunks slot with other request decoding iterations if possible. This figure shows a clear comparison of these past three methods. As we can see, fastest transformer, which is a naive scheduling policy, will block all these new coming instances until all previous decoding phase has been finished. And in VLM and Orca, actually, these two approaches are very similar. It can just, by using the continuous batching, it can directly preempt the previous instance inference process and achieve very high inference batch size by introducing the new incoming input requests of the prefilling phase. And in thoracic serve, it will schedule this computation at a much more fine granularity. And by using the trunk-based design, it can have better SLO guarantee because of the trunk-wise design can schedule the prefilling requests into several pieces at the pieces level, so you can just run them based on the SLO guarantee and the remaining time of each request. And there are some other approaches by introducing some other optimization targets for during the request scheduling. For example, in FastServe, they will prioritize short sequence when scheduling the inference request, because short requests may help the system to improve the overall serving throughput, but it will also sacrifice the experience of the user's long requests. So there is another approach called fairness-aware batching, which tries to make a great balance between different requests based on both their input and output length and their SLO guarantee. The last category of system optimization is called kernel optimization. To reduce the overheads from kernel launching and memory accessing, kernel fusion is widely used by previous deep learning frameworks and compilers, since the backward computation is not required for linear model inference. So there will be more kernel fusion chances in larger models. Basically, existing work in this direction will mainly fuse these kernels from two categories. One is trying to fuse the GMMs with the same shape. For example, this QKV multiplication will be fused together by using a single input matrix. And another category is trying to fuse the 8 bytes with some non-GEMS GPU kernels. For example, the residual connection, the layer normalization, and or the activation functions that can be fused with the add BIOS operator. The second part, which is much more important, is that to make the attention operation running efficiently on GPUs, people have tried to customize the GPU kernels specifically for the attention calculation, and it can be roughly classified into, for example, two categories. One is the prefilling phase. As we mentioned, it's mainly for the input prompts handling, so it will have a very long input sequence. Previously, we are using like cuDNN because it has provided a fused attention GPU kernel. And after that, when linear models are more and more popular, people notice the importance of this problem, and they try to use, like in XFormers, they have already provided an optimization by introducing the online softmax optimization and cutlass GPU kernels, which can help to reduce both the GPU memory overheads and the GPU memory access. So that idea was further introduced in flash attention in a different way, but basically the high-level ideas are similar, and this can accelerate the training process as well as the prefilling phase of the linear model serving process. For the decoding phase, actually the main issue of decoding is because in autoregressive decoding, we are just running some small tensor vector production with matrix, so it's very hard to fully utilize your GPUs. So for example, in flash decoding, they will try to parallelize the sequence length dimension by partitioning the color cache into trunks during the decoding process. It can help to parallelize the memory access of previous generated tokens color cache. And actually, there are some other categories in tailored attention optimization. For example, as we mentioned before, in speculative decoding, the verification can also be optimized significantly, because as we can see in this figure, it shows the roofline model of these 3 stages during attention computation. Decoding attention performance is always underneath the peak bandwidth of the GPUs. That's why we usually say that it's memory bounded. And the pre-feeding attention has higher operational intensity and is under the peak compute performance. So that's why we say it's memory bounded. But for the verification GPU kernel, it can be like memory bounded when the query length is very small, and it can also be memory bounded when the query length is large. So what we want to do is that trying to push this GPU kernel from memory bounded to compute bound by parallelizing the verification process. And another thing worth to be mentioned is another project called Flash Infer. It provides all these previous high performance GPU kernels on pre-feeding, decoding, and verification stages. And it also provides some other optimized GPU kernels for like grouped query attention and quantization-based attention calculation, and also the prefix sharing attention calculation. Another thing is called sampling optimization. We know that by default, language model serving are usually using a greedy-based sampling algorithm, which means we always get the top 1 token during each decoding step. But actually, you can also try to use some parallel sampling techniques like beam search to decode the, for example, top 3 or top 5 output tokens and maintain them during the decoding iterations. And also there are a lot of like stochastic sampling techniques like top K and top P, and temperature controlling can be used to introduce some randomness for more diverse outputs. And these different sampling techniques may also need some specialized GPU kernels during the sampling process. The next part is about the variable sequence length. As we all know that the input length of the LLM serving queries might be different. Some people may have very short inputs, some may have very long document as the inputs. So if we want to batch all these input requests together and using a single GPU core to run all these requests, it will be very difficult because we need to do some like padding or trunking to get like a uniform size of tensors. So to avoid this padding or trunking overheads, some people may have proposed like ragged tensor optimization, which can help to support this kind of computation with minimum padding, and which can somehow improve your GPU utilization. And this is also related to some compiler optimization, because it's very hard for us to write some GPU kernels for all different input length scenarios. So all this index calculation must be done automatically by the compiler. So that comes to our next optimization in GPU kernels, just by using like TVM or torch inductor and even like OpenAI Triton to help us generate these efficient GPU kernels automatically. Basically, most of existing large model serving systems, they will utilize some vendor-specific libraries or manually written kernels as their backend. For example, like Flash Attention, people have used a lot. But in practice, if you want to like change your attention calculation semantics or adapt to some other types of platforms, you need to rewrite the GPU kernels again and again. For example, even you want to enable grouped query attention, you need to understand the whole GPU kernels for the flash attention and rewrite it. So that will be very difficult for most people, machine learning scientists. So that's why we need to introduce a compiler approach. Now we come to the third highlighted research part. It's called Mirage, which is automatically GPU kernel generation system for both machine learning and language models. So today's machine learning models, like language models, are using distributed GPU clusters for both training and serving. And modern GPU platforms are becoming increasingly heterogeneous with new hardware components introduced in each generation. So specifically, this figure shows the hardware hierarchy of a GPU cluster, which includes more than 100 GPUs connected by NVLink and other high-performance networks like InfiniBand. And each GPU will include more than 100 streaming processors, which are the basic compute cores on modern GPUs. And to improve the GPU efficiency and performance, these streaming processors are becoming increasingly complicated and heterogeneous. For example, we have tensor cores introduced in V100 and the sparse tensor cores in A100 and the thread block cluster and the tensor memory accelerator in H100. We will use this group query attention as a motivating example to introduce our work Mirage. Group query attention has been widely used by recent language models to reduce the kernel cache overhead by allowing each key and value head to be shared across multiple query heads. Well, this group query attention can be expressed in a few lines of PyTorch code. Here, we only use 3 lines. Right? We can directly run the program in PyTorch and will result in separate GPU kernels for executing matmos and softmax. So this approach achieves suboptimal performance due to missing a variety of advanced GPU optimizations, such as kernel fusion and algebraic transformation, like reusing shared memory and tensor memory acceleration. So to enable optimized attention kernel calculation, existing systems rely on users to manually implement GPU optimization in C++ or Python. And enabling GPU optimizations involve around, for example, 7,000 lines of code in CUDA or 700 lines of Python code in Triton. This slide shows the code snippet for implementing flash attention in Triton, which appears to be non-trivial for machine learning engineers with limited GPU expertise. And especially, we observe that existing GPU or Triton approach involves 2 limitations. First, it will require manually design and implement of GPU optimizations at the kernel, thread, block, and thread levels, which turns out to be hard for non-GPU experts. And the second thing is, as we mentioned before, implemented programs only work for standard attention kernels and does not support emerging attention variants, such as sparse attention, latent attention, and others. So we have recently developed Mirage, which is a super optimizer for language model. And the key idea behind Mirage is to automatically generate high-performance GPU kernels without relying on the GPU expertise to manually design and craft potential optimizations. And it will offer 3 key advantages. First, it requires significantly less engineering effort. For example, to optimize the attention computation, you only need to write a few lines of Python code to describe the attention computation instead of writing 7,000 lines of CUDA code. And Mirage will automatically generate the highly optimized GPU kernels for the desired computation. Second, Mirage can also realize better performance. It will outperform existing systems such as Triton and Flash attention by up to 3 times on some specific attention kernels. And the last thing is that Mirage will not rely on manual implementation and offers day zero support for new machine learning models. So in Mirage, we introduce a new representation called Mu graph to describe the potential optimizations at different levels on the GPU hierarchy. In particular, each mu graph has a single kernel graph that describes the computation at the kernel level. Where here each vertex represents a GPU kernel running on all streaming processors of a GPU, and it can represent a standard tensor algebra kernel such as MathMore and ReDuce, supported by vendor libraries used like cuDNN and Nico. Alternatively, a vertex can also represent a customized kernel like Flash attention. And this operator called graph-defined operators. Second, each thread block graph describes the computation of a thread block running on a single streaming processor. All intermediate results in this thread block will be saved in the GPU shared memory to maximize and enable the shared memory usage and minimize the data transfer overheads. Similar to kernel graphs, the vertex in a thread block graph represents the computation within a thread block, and it can be like standard tensor algebra operator supported by like Catalyst or customized operators whose definition is captured by a lower level graph, which is a thread graph in this case. This multi-level graph implementation allows Mirage to discover both algebra and schedule optimizations at the kernel, thread block, and thread levels of the GPU compute hierarchy. And existing highly optimized GPU kernels are specific mu graphs in Mirage. So in this figure, we show that how group query attention is executed in PyTorch if we only describe by using the PyTorch level without implementing the corresponding GPU optimizations. PyTorch will launch separate GPU kernels for the MathMore and softmax execution, and it will also miss many potential GPU optimizations like shared memory reuse and kernel fusion. By using Mirage, we can actually support some existing machine learning systems like optimizations like Flash attention and Flash decoding. These kernels are designed by GPU experts, but here we show like how we can represent this Flash decoding in mu graph. Here we organize the attention computation into 2 kernels, as shown in the 2 thread block graphs, and it will decompose softmax into element-wise exponentiation, 3 summation, and element-wise division, which are highlighted in the orange circle in this figure. And it then applies algorithm transformation to reorder a matrix multiplication and the element-wise division, which allows the first kernel to perform 2 matrix multiplication by saving the intermediate results in GPU shared memory. And this figure shows the best mu graph discovered by Mirage for group query attention, which is like 2.2 times faster than Flash decoding kernels by using 2 additional GPU optimizations. First, Mirage will not use the repeat operators to replicate the keys and value sensors. Instead, we will introduce a reshape operator in the thread block graph. And these changes are highlighted in the orange color blocks. And second, the reshapes are also making Mirage to perform larger metric multiplication within a thread block. And as a result, we can use the tensor cores more efficiently. Now let's take a look at how Mirage will automatically generate optimized kernels from end to end. So here is an overview of Mirage, and we take a PyTorch program as an input, and it will automatically generate a variety of mu graphs that may be like functionality equivalents to the input programs. Next, the generated mu graphs are sent to the equivalence verifier to verify the correctness of these mu graphs. Finally, all these verified mu graphs are sent to the mu graph optimizer to further optimize their performance, and as a result, the best mu graph is used to generate the final GPU kernels. There are two key challenges we need to address in Mirage. The first is how to generate potential mu graphs, and the second is how to verify their correctness. Mirage uses two techniques to address its challenges. First, we use expression-guided search to quickly discover the potential mu graph. And then we use probabilistic verification techniques to verify the correctness of these mu graphs with strong theoretical guarantees. The first part is the graph generator. Mirage's mu graph generator will take an input as a PyTorch program and search for mu graph functionally equivalent to the input by using the available operators at the kernel thread block and thread levels. And Mirage will explore an extremely large search space of these potential mu graphs to discover the optimized solutions. To accelerate the search procedure, Mirage will introduce a novel tensor representation called abstract expression to prune the search space. Abstract expression is based on observation that we don't need to consider mu graphs whose intermediate results cannot contribute to the final results. For example, if we use the attention program as an example, the mathematical formula for the attention calculation is like this: the product of QK softmax and then product with V. When we search for the potential mu graphs for attention, we should continue the search when encountering the first mu graph, since multiplying QK can help contribute the final result. But if we encounter the second and the third mu graph in this figure, we should stop the search progress because multiplying Q and V or computing the exponential of Q cannot contribute to the final output. Based on this observation, we introduce the abstract expression to represent a tensor computation while extracting away index details. Specifically, this figure shows that the abstraction expressions for all intermediate results. And you can see that the abstract expression for each intermediate tensor can help contribute to the final results. So to formalize this idea, Mirage uses first-order logic to reason about the relations between abstract expressions. We model two relations here, the first is the equivalence and the equivalence relations, and the second is the some expression relations. And these relations can be used to verify the correctness at last. And the abstract expressions are leveraged by Mirage to guide the search and prune the intermediate results. But they can, for example, in this case, mu graph G1 can be used to construct G2. And G1 is some expression of G2. Based on the key property, Mirage will directly influence all the mu graphs whose expressions are not sub-expressions of this final result. So this prune technique will improve the scalability of the search algorithm and allow Mirage to discover highly optimized solutions. The next part is the verifier, which means Mirage needs to verify whether each discovered mu graph is functionally equivalent to the input program. So here we use a probabilistic equivalence verifier that will perform random tests over the finite fields to examine the equivalence between mu graphs. For example, Mirage will generate randomly initialized input tensors and send them to both mu graphs in this figure, and it will check whether these two mu graphs perform identical output tensors. So all these computations are performed in a finite field to avoid floating point errors and integer overflows. So these random tests are also offering very strong theoretical guarantees. Specifically, equivalent mu graphs always pass random tests, so this test would not introduce any false negative. For non-equivalent mu graphs, they will fail at a certain random test with a certain probability, and Mirage will repeat this very cheap random test to make sure the random tests are processed. We have compared with the Mirage and with other machine learning compilers and some human manually written GPU kernels on a variety of workloads, like multi-head attention, group query attention, and multiple query attention. And in this figure, these are very commonly used attention variants. And we also evaluate the incremental decoding, speculative decoding, and the prefilling phase separately because they are different phases during the inference process. And these figures compare with Mirage with flash attention, TensorRT, PyTorch, and Triton on A100 GPUs. And the takeaway is that Mirage can consistently discover more optimized GPU kernels than these existing compilers and some hand-optimized GPU kernels, resulting in up to 3.5 times speed up. So if you are interested in why Mirage generated kernels outperform existing one, especially for the human expert writing kernels, this slide shows that the best mu graph discovered by Mirage for LoRa, which involves 3 matrix multiplications and an element-wise addition. Mirage can automatically discover a mu graph that fills these 3 math-mods and addition into a single kernel, which is internally performs 2 math-mods at the thread block level to more efficiently use tensor cores on modern GPUs. And Mirage is public available and easy to use. You can directly call Mirage super optimizers to generate the optimized mu graphs for any PyTorch input program. And it can also support JIT compilation where Mirage JIT compile an optimized graph to generate the GPU kernels. And the optimized graph can be directly used as a PyTorch operator. Okay. Basically, that's all for today's classification of existing optimizations for language model serving. The next part is software frameworks. We have compared with some state-of-the-art language model serving system, especially for the open source GPU-based solutions, and summarize their difference in several aspects in this table. And this table was made half a year ago, so there might be some updates of these open source projects. But we still want to highlight a few aspects. For example, some of these systems that doesn't support the pipeline parallelism because of the latency requirements. And you can also see that these different systems are using totally different GPU kernels for their attention calculation. And things might have been changed during the past half a year, but basically these choices are determined by their different optimization target. Some systems like SpecInfer are prioritizing the end-to-end inference latency, so the GPU kernels will be totally different from those like VLM who are prioritizing the inference throughput. There are also some other types of features which is optimized by the systems, and more details can be found in our survey paper. At last, I want to introduce some of the future directions in LLM serving system optimization. The first thing is about the development and enhancement of the hardware accelerators. This figure on the left shows the several types of optimizations provided by NVIDIA's H100 GPU. If you compare it with previous A100 GPU, you can find that it has much more streaming processor, and it introduced some new tensor cores, and also it introduced the transformer engine optimization, which is specialized for language model serving. And by summing up all of them together, we can achieve like 6 times speed up. And another very important thing we need to know is that considering the memory bounded operations during serving, more and more accelerators are trying to improve their memory access bandwidth. For example, in NVIDIA's GPUs, we can find that they are continually increasing the memory bandwidth to help increase inference efficiency. The second part is about the efficient and effective decoding algorithms. We believe that, for example, speculative decoding can be a very promising alternative solution because it will not change the generation quality of the language models, but it can directly bring some accelerations. And we can also find that in the past few months, speculative decoding approaches are widely studied by communities, and there are more and more people are trying to, for example, using some alternative speculators to replace the small model. For example, we can combine the other types of acceleration we mentioned before, for example, the non-autoregressive decoding algorithms, and use them as a speculator to generate the draft tokens. That's also something has been done in look ahead attention. And also we can use the large model itself, but introduce the early exiting mechanism to run a few layers and as the draft tokens and verify them. So that's the second part. And the third part is about the long context or long sequence scenario optimization. We have introduced a lot of system level optimization, such as the memory management or distributed sequence parallelism approaches to parallelize the long sequence handling. But here, what I want to mention more is at the algorithm level. People have already found some issues when generalizing the language models to long context scenarios. For example, there's a very famous loss in the middle test, and we can find that some very famous like GPT-4 models have also have these problems. It will miss some information when the context is too long. So I think there might be some problems we need to solve from the algorithm level. One promising solution is by using the retrieval augmented generation techniques, and it can manually select some relevant documents or context information during the decoding process. And we have also proposed speculated RAG work in this year's ICML. And if you have any interest, welcome to our poster. Okay. And the next part is about investigating alternative architectures. For example, we have mentioned some other types of architectures in our previous slides, like using MOE or state space models. And I think maybe in the future, a more promising direction is trying to use some attention-free methods because they are much more friendly to to GPUs, and that may also totally change existing trend of the hardware development. And the last part is about the exploration of deployment in complex environments. For example, we have mentioned about like using preemptible instance or decentralized computing resources to run language models, which aims to provide lower cost and make language models more affordable for more and more people. And the last point is about the automatic adaptation to adaptation to specific requirements. For example, one trend today is that people are using large models in more and more different ways. For example, by using large model as agents, we can enable them to interact with each other. And that's a very simple case. In more complicated case, we can further like the agent to learn from the communication process, which means that during the interaction process, some parts of the models may need to tune their model weights and for better model performance. And also another thing we need to know is that today people are trying to fine-tune this model by using parameter efficient fine-tuning techniques like LoRa adapter, which means that the base model parameters will be freezed and it will be shared across different LLM agents. So considering all these factors, if you want to design some learning model serving systems to support the execution or simulation of these scenarios, it will be much more complicated compared with just run a single language model with your system. Here we want to introduce one last highlighted research is called Flex LLM, which aims to provide a co-serving system for both inference and parameter efficient fine-tuning. The motivation is that today we have provided a lot of different frameworks for the whole language model life cycle. For example, for pre-training, we have Magnetron, we have DeepSpeed. For parameter efficient fine-tuning, we have Hugging Face PFT library. We can also use PyTorch. But for serving, we have introduced a lot of related topics today. And for specifically for the language models with like parameter efficient adapters, there are also a lot of work as in this direction, like LoRa and Polyka, which aims to serve, for example, hundreds or even thousands of parameter efficient adapters simultaneously, but allowing them to share the same model weights. But here, what we found is that for serving workloads, as we mentioned before, it's usually memory bounded because of the autoregressive decoding. But for the fine-tuning process, it's more compute bounded. That means that during the fine-tuning process, your GPU memory bandwidth is not fully utilized, which seems provide us a chance to fuse them together and achieve better GPU utilization. So that's our proposal. We want to build a language model co-serving system to improve the utilization for both fine-tuning and inference. Okay, maybe you have heard about some papers about machine learning scheduling systems. Actually, previous approaches usually do not share resources between training and inference because they have diverse compute logics and performance requirements. The opportunity here is like one thing is that, as we mentioned before, parameter efficient fine-tuning will enable the model to share the base model weights with the inference process. And also another thing is that its weights will not be updated during its base model's weights will not be updated during fine-tuning. So that makes it possible to share weights and fuse operators between different tasks. This figure shows three methods for parameter efficient fine-tuning. Traditional full fine-tuning approaches will involve updates billions of parameters, which can be memory intensive and environmentally costly. So by using like LoRa adapters, we can just update 1% of the total model set parameters, and the rest 99% base model parameters will not be updated. To utilize this property, we propose Flex LLM, co-serving systems, and it can save a lot of GPU resources, achieve higher GPU utilization, and preserve the inference LO. To achieve these targets, the key challenge here is the mismatch between the inference and fine-tuning process. The execution of LLM inference is much more fine-grained. So like we mentioned before, each step only takes dozens of milliseconds. But fine-tuning process can be much more time-consuming because in each step it will handle a very long sequence with like dozens of input tokens, and it can be more time-consuming because of the backward propagation. So to solve these problems, we propose a token-level fine-tuning and the graph pruning individually. Eventually, by introducing FlexLM, we can achieve pretty low per iteration latency like inference, but also finish the fine-tuning process. So let's start from the first technique. The key idea of token-level fine-tuning is to decompose the sequence-level fine-tuning into the granularity of tokens, including both the forward pass and the backward pass. Existing systems usually generate gradients for all tokens in a sequence with one pass of backward propagation. We show that for generative language models, actually we can do the backward propagation token by token, but in a reverse order. One thing might be complex is attention calculation, where each generated token relies on the information from all previous tokens. It also means that during the backward, each token will also contribute to all previous tokens' gradients. So therefore, we propose to accumulate the gradients of previous tokens instead of directly backpropagating them. This process will continue until the backward traversal of all tokens in the sequence is completed. Such token-level fine-tuning process will help to achieve similar per iteration latency as inference. Another big issue is that the fine-tuning memory overheads. We show that even for a single request, it requires more than 70% memory space than the inference because existing fine-tuning system stores all the activations for backward. So our insight here is that actually you don't need to store all of them because only a small fraction of the model parameters will be updated, like the LoRa components. So we can optimize the computation graph to point the edges that may not be reused during the backward execution. For example, the gradients of the base model parameters can be removed. Similarly, the input of linear layers can also be released because we don't need them to calculate the gradients of activations. So we can also involve some other memory optimizations. By summing them together, we can achieve a very high memory reduction end-to-end. The basic workflow of FlexLM is trying to get the input graph of the input programs of the language model, and then we can use the PFT compiler to parallelize the input computation graph and point the graph based on to reduce your memory overheads. And then we will introduce a request scheduler to schedule the fine-tuning process at the token level and mix it up with inference workloads. And then we introduce another distributed code serving runtime to run these different tasks together. We evaluated these systems on Llama model on 16 A100 GPUs. Compared with using separate systems and GPUs, FlexLM can achieve very similar parameter efficient fine-tuning throughput for light inference workload. If we increase the inference arrival rate, which means you need to assign more GPUs to inference tasks in the separate setting, and we can find that we can achieve higher fine-tuning throughput speed up because we mix them together. And if we continually improve the inference arrival rates, you can see that it can no longer make any progress by using the separate setting because the rest GPUs are not enough to support the inference process. But we can still achieve some speed ups. We can still achieve some throughput in FlexLM. That's basically all the main content I want to share in today's talk. And one last thing I want to mention is that, as we mentioned at the very beginning, we categorize all these existing techniques into algorithm and systems. But actually, what we want is that when we are trying to optimize the language model serving system, we need to combine them together and make some code design to jointly optimize the end-to-end inference process. So I think that's something we should keep in mind, no matter on you are a system developer or algorithm scientist. And in today's talk, we have briefly introduced 4 of our highlighted past research, including SpecInfer, SpotServe, Mirage, and FlexLM. And all of them have been open source, and you can also find these papers on arXiv if you are interested. That's the end of my today's talk, but before the ending, I would like to acknowledge my previous postdoc advisors, Zhihao Jia and Tianqi Chen, and who are the assistant professors at Carnegie Mellon University. And I also want to thank many other colleagues in our lab, like some undergraduate students, master students, and PhD students. And we have also a lot of internship students from the other universities around the world. So this tutorial cannot be made without their efforts. And by the way, we are also actually looking for prospective students. So welcome to join us if you are interested in building language model serving systems or just machine learning systems. Thanks for your listening. Okay.
Thanks. This was very informative. Since I'm just one person with one mic, I'm asking people to put their questions on Rocket Chat, barring technical difficulties. Otherwise, I can just ask my own questions. So, all right, Maria Gorinava, she, her, thank you very much for this insightful tutorial. You mentioned a lot of different methods and tools for optimization at various levels. If you could recommend one library or tool that offers reliable and robust set of optimizations for practitioners in industry, which one would it be?
I think it depends on your personal requirements. But for example, if you are looking for some high performance serving kernels, I think Mirage is the best you want to choose. But if you are looking for like more documents and easily deployed solution, I think VLM can be a very great solution.
Okay, so you mentioned some approaches that assume conditional independence between the output tokens. And I was just wondering, conditionally independent on what? Conditionally independent given the observation?
You mean for the non-autoregression decoding? Yes. Can you repeat the...
So you said that it's assuming conditional independence between output tokens. Conditioned on what? Conditioned on the observation?
No, it's conditioned on the previous generated tokens. By default, if you are using autoregressive decoding, which means that the next token's prediction will depend on all previous generated tokens. But in the non-autoregressive decoding, for example, if you are just want to output the next 3 tokens, all these 3 tokens will be independently determined by previous tokens. But for these 3 tokens, they have no relationships or dependencies on the probability distribution.
Okay, so they're conditionally independent given past tokens.
So you talked a little bit about speculative decoding. I was wondering, like, when we do these tokenization, right? We generally use words as tokens, but when we learn languages, we basically learn in phrases. So does it make sense to like basically use phrases as tokens and like train the LLMs using that?
You mean letting them using different number of tokens or different types of tokenizers?
Saying that can we change the way we think about tokens, like from words to phrases, right?
Yeah. The number of it's a very great question actually. We didn't go through details, but we briefly mentioned that in our like tree-based speculative decoding approach, how to expand the token tree is an open problem, which means that the size of the token tree is also worth to be explored. In your problem, which means that, for example, we just use a sequence as a token tree structure, the sequence length will be the tree size, right? So, for example, if your small model is very powerful to like predict the next 5 tokens, it will be better have a longer speculation length. But in practice, it's very hard because due to the dependency of as we mentioned before in the autoregressive decoding approach, the accuracy of the speculation will be decreased exponentially with respect to the output length. So in practice, we try to increase the tree size, but for the depths, it's usually like at most 5 or 10. So it will not be too long at each step. Yeah, but think about if you can achieve like 5 times speed up, that's already very significant. Yeah. Okay, thanks.
You talk about the attention mechanism replacement. How do we make sure the 2 attention mechanisms, they are the same, so we can safely replace that?
You mean which and the speculation and the default?
Say in one of your chat, you talk about, say we want to replace the naive attention mechanism to more efficient attention mechanism. So this equivalence. So how do we make sure when we replace the more efficient attention mechanism, mathematically they are almost equivalent to the original one?
I see. Yeah, so for like, we mentioned about the equivalence in several approach in this tutorial. The one thing I think is most related to your question is the speculative decoding part, because the speculation decoding can like guarantee the correctness by using the original large model as a verifier, which means that, for example, if you cannot obtain the same output, the large language model will tell you that, for example, the third token is not correct, and all the tokens after the third tokens will be just directly dropped. Only the first 2 correct tokens will be sent back to the small model as the next step for the speculation. So that somehow guarantees the correctness. And this correctness is at the output level. It's not mean like in our like Mirage paper, we try to optimize the program. It not just guarantee the correctness at the output level, it also guarantees at the intermediate result level. In speculative decoding, the small model's intermediate results can just be random tokens. It can be a lot of incorrect results. So it's fine, but because the large model will help to verify the results.
I see. And when you say the same, it means output the same. That means they are exactly the same, or
exactly the same.
Exactly the same. I see. Okay. Thank you.
Okay, thanks.
So since we started 2 minutes late, I'll take this last question from the chat. Zhang. Thanks for the great talk. For SSMs like Mambo, will current inference frameworks and algorithms continue to work, such as continuous batching and speculative decoding?
I think no, actually, because some of the current state-space models and other like RWKV or RedNet, these algorithms or model architectures are based on some recurrent units, which are like they are running the model sequentially, and it may not be like the same as the current transformer models, but the high level I think the continuous batching can still work actually, because even for this state space models, you still need to like considering the batch execution at the GPU kernel level. But I'm not sure if the speculative decoding can work, or you can just change the model structure to make it fit to the speculative decoding approach.